Hi guys, in this lecture we will continue from where we left off. We will look at some more type of problems that can be asked in GATE based on transformers. So the first topic that we will be taking today is all day efficiency. Now as we saw, efficiency is how it is given by eta is equal to x into kVA cos phi by x kVA cos of phi plus pi plus PCU. But that is the efficiency at any instant when the loading is constant. But if we practically see, the load can vary throughout the day. That means it is more practical to calculate the efficiency of the entire day. But when time is taken into account, we cannot directly bank upon the power. Rather, we have to take into account the energy. So, eta all day is nothing but energy output by energy input into 100%. The unit of energy would be kilowatt hour. Okay. So that is how we calculate the all day efficiency. Now during all day efficiency, as the load is varying, the core loss, it is not a function of load. So it will be taken as constant, whereas the copper loss is a function of load. So it will vary as the load changes. And we know copper loss is proportional to current square. So it will vary as x square or the loading square. So let us consider the problem that is given to us. It is saying a 6 kVA transformer has a core loss of 50 watt and full load ohmic loss of 120 watt. The daily variation of the load on the transformer is as follows. So I can assume throughout the entire day, the core loss will remain as 50 watt. But as you can see, there are different load during different intervals, which means the copper loss will change. So I have to consider each and every interval separately. Now 8 am to 1 pm. We know that copper loss is proportional to x square. So what is the load here? First of all, we have to find the kVA, that is P by power factor. It will come out to be 3.75. Now full load is 6 kVA and the copper loss at full load is 120. So what is the copper loss here? 120 into x square. What is x? Fractional loading, which is 3.75 by 6 whole square. So this will come out to be 46.875 watt. Similar procedure you have to follow in other intervals. 1 pm to 8 pm. What will be S? 4 upon 0.6. It will come out to be 6.67 kVA. It is 3.75. So what will be copper loss? 120 into 6.67 by 6 whole square, which will come out to be 148.148. Then it is from 8 pm to 11 pm. Again we will find S. The power was 2. Power factor is 0.9, that is 2.22 kVA. So what is copper loss? 120 into 2.22 by 6 whole square, that will come out to be 16.46 watt. Then 11 to 4. S will be 1 by 0.1, that is 10 kVA. So what will be copper loss? 120 into 10 upon 6 whole square, which will come out to be how much? 333.33 watt. And since 4 am to 8 am there was no load, so copper loss would be 0. Now once we have got copper loss, we have to convert it to energy. So first let us find out the output energy. How will be the output energy? It will be based on load. 3 kilowatt for 5 hours, then 4 kilowatt for next 7 hours, then 2 kilowatt for 3 hours, then 1 kilowatt for 5 hours. How much it will come out to be? 15 plus 28 33 plus 6 39 plus 5, sorry, 15 plus 28 43 plus 6 49 plus 5 54. 54 kilowatt hour. What about core loss? It was 50 watt or 0.05 kilowatt for 24 hours. So 24 into 5 is 120, that is 1.2 kilowatt hour. Okay. Then what about copper loss? For that again you have to multiply different copper loss for the duration that they have occurred. So what will be copper loss? Initially it was 46.875 for 5 hours. Then it was 148.148 for the next 7 hours. Then it was 16.46 for the next 3 hours. Then it was 333.33 for the next 5 hours. After that it was 0. So it will come out to be 2.987 kilowatt hour. Now once we have losses as well as the output energy, eta will be output energy by output energy plus losses 2.987 plus 1.2. This will come out to be 0.928 or we can say 92.8%. So that is how you calculate the all day efficiency of a transformer when the load is varying throughout the day. Moving on to the next category, next we have voltage regulation. Now voltage regulation can be of two types. One is called as regulation down, other is called as regulation up. It will be no load voltage minus full load voltage by no load voltage. This will be no load minus full load by full load. Okay. So this is general definition that we use in most of the cases, that is no load minus full load by full load voltage, but both are equally valid. Now when we have to find the voltage regulation, the norm is it is calculated at the output side, so mostly we will calculate it on the secondary side of transformer. But as we very well know, we can refer the circuit to either secondary or the primary side, so you can calculate the voltage regulation on either side of the transformer. Is it fine? So now what we have to do is to calculate voltage regulation. If you have referred the circuit to the secondary side, you will find like this: mod E minus mod V by mod V into 100%. Mod E is the induced EMF, mod V is the terminal voltage. Okay, that is how you have to calculate. But in case of transformer, by approximation, we can also write it as mod I by mod V R cos phi plus X sin phi, or you can say plus minus, plus for lagging power factor, minus for leading. But remember, this approximation you better only use in transformer, not anywhere else, because this is very crude approximation. This is valid for transmission line as well as synchronous machines, but it will give inaccurate result in those two cases. But in transformer, the result is almost accurate. Is it fine? So let us see the problem that is given to us. Or let me also tell you one more formula. Voltage regulation can also be written as mod I R cos phi plus X sin phi, where I is in PU, R is in PU, X is also in PU. This formula can also be used. Now see, it is saying 100 MVA 230 by 115 kV delta delta 3-phase transformer has per unit resistance of, that is RPU is given to us, per unit reactance of XPU is given to us. The transformer supplies a load of 80 MVA. Power factor is given to us 0.85. We have to find the percentage voltage regulation. Now this has to be converted into PU before finding the voltage regulation. So as you can see, the rating is 100 MVA. So 80 by 100 is 0.8 PU. That will basically be equal to mod I in PU. Why? Because voltage is taken as 1 per unit. So current in PU will be same as the power in per unit. Now, when you calculate voltage regulation, 0.8, 0.02 into 0.85 plus x will be 0.055 into sine of phi. How you can calculate sine of phi? First calculate phi from here, then sine of that. So it will come out to be 0.0367, or it will be 3.67%. Moving on to next problem based on voltage regulation. A 25 kVA 2000 by 200 volt 50 Hz transformer has maximum efficiency at 80% of full load. That is, loading for maximum efficiency is 0.8. Now RPU is 0.012 and ZPU is 0.05. Okay, remember here it is impedance, not reactance. So you might be committing an error. Now we have to find efficiency and voltage regulation at half of the full load and 0.8 power factor lagging. Okay. So now the full load copper loss, that is I full load square into R. Okay. That will basically be equal to R PU. Why? Because full load current in per unit is 1 PU. That means indirectly I have been given the full load copper loss. Now I know that maximum efficiency condition is under root P core by P CUFL, that is 0.8. So 0.64 is equal to P core by 0.012, which means the core loss will come out to be 7.68 into 10 to the power minus 3. Now once I have achieved the core and the copper loss, I need to find the efficiency at half of the full load, 0.8 power factor lag. Now what is the method of finding efficiency? X, that is 0.5 because half of the full load. kVA is 1 PU. Power factor is 0.8. 0.5 into 0.8 plus copper loss is 0.012 into x square. We know x square into PCUFL plus core loss is 7.68 into 10 to the power minus 3. So this will come out to be 97.4%. Now when we talk about the voltage regulation, for that we need R and X. How you can calculate X? Under root Z square minus R square, 0.05 square minus 0.012 square, which will come out to be how much? 0.04854. So when you calculate voltage regulation, you are calculating at half of the full load. So I will be 0.5 PU. R is how much? 0.012 into cos phi, 0.8. 0.04854 into sin phi, that is 0.6. So this value comes out to be 0.0193, or we can say 1.93%. Next, move on to the next kind of problem that we can face, that is your three-phase transformer. Now mostly in the recent years it has been seen that the problems in three-phase transformers are centered around the phasor diagram. Other parameters of three-phase transformer such as efficiency, voltage regulation, equivalent circuit are same as that of a single phase transformer, but you have to take care of two things. On star side, line current is equal to phase current. Line voltage is equal to root 3 times phase voltage, and it leads by an angle of 30 degree. That is for positive sequence. Otherwise, line current is equal to phase current. Line voltage is root 3 times phase voltage, but it lags by an angle of 30 degree for the case of negative sequence. For delta connection, line current is equal to root 3 times phase current, and it lags by an angle of 30 degree, but line voltage is equal to phase voltage for positive sequence. For negative, IL is equal to root 3 I phase at an angle of plus 30 degree, and line voltage is equal to phase voltage for negative sequence. So this much you should always remember. Other than that, all the parameters are same as that of a single phase transformer, like efficiency, voltage regulation, etc. So our major focus should be on understanding the phasor diagram. Now while drawing the phasor diagram, you have to take care of the corresponding terminals on primary and secondary, A1 and small a1, A2 and small a2. So the first thing that you have to do is, you have to draw the primary phasor. Since it is a star connection, the phasor will also be in the form of star, like this. Okay, the outer terminal is A2 and the inner terminal is neutral, or we can say A1. Now we are drawing for positive sequence. If it is not mentioned, you will always draw for positive sequence. So phase B will lag phase A by 120 degree. So this will be phase B, and phase C will lag phase B by again 120 degree. This will be phase C. Now based on primary phasor, we have to draw the secondary phasor. Now capital A1 to capital A2 is vertically upwards. So small a1 to small a2 will also be vertically upwards, like this. And small b1 to small b2 will be in the same direction. But here if you see, B2 terminal is connected to A1. So you will draw like this, but B2 and A1 should be same. Okay. Then C1 to C2 will be in this direction. But here if you see, C2 is connected to B1. So like this, C1 to C2. Now if you see, the output is taken at A2, B2 and C2. So when you draw reference phasors in delta, it will be based on 2. So this will be A, B, C. Because here is A2, so I will mark it as A. Now if you see, this is the vertical, this phasor, and this is like this. So capital A, or the primary phasor, is vertically upwards, and the secondary phasor or small a is 30 degree lagging. So this connection can be called as YD1, because on a clock it will look like as it is 1 p.m. So remember, the secondary phasor on a clock represents the hour hand, and primary phasor represents the minute hand. So usually, or in every case, you have to keep the primary phasor vertically upwards so that it points to 12, and then we will determine the secondary phasor. Let me show one more problem based on this. Here it is saying, for delta star transformer, connection and terminal markings are shown. If 1 and 2 represent the positive and the negative sequence, then correct solution in PU for VA1 and VA2. VA1 is nothing but the primary voltage for positive sequence. VA2 is the primary voltage for negative sequence. Now first of all, we have to draw the primary phasor. So remember, I am drawing like this. So if you see, I am going from a undotted terminal to a dotted terminal. Is it fine? So this will be, suppose I draw VAB. Okay. Now when we are drawing for positive sequence, BC will lag AB by 120 degree. So it will be BC. And AC will lag BC by again 120 degree. So this will be CA. But now if you draw the reference phasor, what you will get? We will get something like this. As we can see, the primary phasor capital A is not vertically upwards, but it should be vertically upwards. So what I do is, I will rotate this triangle. If you rotate this triangle, what you will get? You will get a figure like this. This will be A, this will be B, this will be C. And these will be the reference phasor. Once I have gotten this, I can draw the secondary phasor. How? In such a scenario, you have to judge which winding in primary and secondary are parallel. As you can see, these two are parallel, which means while drawing a phasor from undotted to dotted, the same phasor will be here from undotted to dotted. But here we have to draw from dotted to undotted, that is from neutral to C, because I want to find VCN. So if you draw opposite, you have to change the phase. Okay. So this one is what it is. This is AC between A and C. So we will draw opposite to this like this. Why I am drawing like this? Because I am drawing from N to C, that is from dotted to undotted. So it will be opposite to the primary phasor. If you keep same orientation between primary and secondary, phasors will be parallel. If you oppose the orientation in primary and secondary, the phasors will be anti-parallel. As simple as that. Now here if you see, this horizontal winding is parallel to this, which means when you are drawing the phasor like this one, the primary phasor will be opposite, because again I will draw from dotted to undotted. So it will be like this. Similarly, B will be like this. Now if you see, capital A is upwards whereas small a is left. So VA1, how you can obtain from small a? By 90 degree clockwise rotation. 90 degree clockwise means minus J. Now why there is no magnitude change between primary and secondary, though there will be turns ratio? It is because we are talking in per unit. In per unit, the magnitude remains same on primary as well as secondary. Now let us try to draw for negative sequence. For negative sequence, what you will do is, first suppose you draw for AB. Now after AB, you have to draw CA lagging AB by 120 degree, because the phase sequence in negative sequence will be AB, CA, BC. That is your negative sequence. So if you have to draw CA lagging by 120 degree, how you will draw? You will draw like this, CA. Then you will draw BC. Okay, AB, then CA, then BC. Now if you see, A is vertically upwards, this is C, this is B. Now when we draw for secondary, we have to draw anti-parallel to primary. We just now saw. So CN is anti-parallel to CA. CN is anti-parallel to CA. So this will be CN. Okay. Then this AN. AN is anti-parallel to BC. AN is anti-parallel to BC. So this will be AN. Then this will be BN. Now if you see, capital A is vertically upwards whereas small a is horizontal. So how you can obtain capital A? VA2 is J times VA2. 90 degree anti-clockwise, which means multiplication by plus J, which means our option C is correct. That is how we can relate the primary and the secondary phasors. Moving forward, this is one of the previous year questions that is very good. So it is saying, figure shows a delta star connected three-phase distribution transformer used to step down the voltage from 11,000 to 415 volt line to line. Which means As I told you, in delta, the line voltage and phase voltage are equal, that is 11,000 volt. But here in star, the phase voltage will be line upon root 3, that is 240 volt, that is 415 by root 3. Always remember, V phase primary by V phase secondary, that is basically equal to the turns ratio. So turns ratio is basically equal to ratio of the phase voltage. Now it is saying under normal conditions switch S1 is closed while S2 is open, but under certain special condition S1 is open while S2 is closed. Now if you see, as soon as you close S2, this winding gets shorted. If this winding gets shorted, which means suppose this is N, the voltage on secondary VBN will also be 0. Here we will apply 11 kV. So what we will get here? The secondary voltage will be 240 as we have seen. So phase voltage will be 240. Now, since the primary winding is in delta, we can say the sum of voltages will be 0. We know that VBC is 0, so VCA is equal to minus VAB or minus 11 kV. Since their voltage here is minus 11 kV, it means the voltage on the secondary side will also be reversed in polarity, minus 240. So if you now find out VAC, it is VAN minus CN. 240 minus minus 240 will be 480. So our answer will be B. Okay. So remember, in delta, whenever you take sum of the line voltages by KVL, it is bound to be 0. That is why there is no zero sequence voltage when we talk about delta. Next is, let us talk about the next concept, that is auto transformer. So usually we connect a two winding transformer as an auto transformer. So there are two types of polarity. One is additive, the other one is subtractive. Additive is when two voltages will get added up to form one voltage of the auto transformer. Subtractive when they get subtracted. So here in auto transformer, you have to find the ratio K, which is the ratio of low voltage to high voltage. But that is low voltage upon high voltage for auto transformer. Now rating of auto transformer is basically rating of 2 winding by 1 minus K. That is one of the most important concept when you have to deal with a auto transformer. And the other thing is that you can assume that the loss will remain constant when we generate a auto transformer from a 2 winding transformer. Though it is not practically true, practically the losses change, but we have to consider them as constant. Is it fine? So now let us see what it is talking about in this problem. It is saying a 400 by 100 volt single phase 2 winding transformer is to be used as an auto transformer to supply 400 volt from a 500 volt source, which means the ratio of low voltage to high voltage is 400 by 500, or we can say 0.8. Now it is tested as a 2 winding transformer at rated load 0.8 power factor lagging, and its efficiency is 0.95. So what is 0.95? Efficiency at rated load and 0.8 power factor lag. Plus there will be certain loss. So what will loss come out to be from here? Loss will come out to be 0.0421 pu. Okay, here I am solving in pu. Since the rating is 5 kVA, what is the actual value of loss? 0.0421 into 5, which will be 0.2105 kilowatt. Now, while finding the efficiency of auto transformer, I need to know the rating of auto transformer. That is rating of 2 winding by 1 minus K. What is the rating of 2 winding? That is 5 kVA. 1 minus K is 1 minus 0.8. 5 by 0.2, 25 kVA. We need to find the rating of efficiency of auto transformer at rated load 0.8 power factor lagging. So that is 25 into 0.8. I am talking in absolute values. 25 into 0.8 plus losses shall remain same, 0.2105. So how much will this come out to be? 98.95%. So that is how you calculate the efficiency of auto transformer when you already know about the efficiency of the 2 winding transformer. The other type of question that can be framed from auto transformer is based on the current that are flowing in different parts of the winding. For that, let us look at this problem. It is saying two resistive load R1, R2 each of 200 ohm are supplied with 100 volt and 300 volt from a 400 volt supply using an auto transformer. We need to find the current in the windings. Here you know voltage is 100, resistance is 200. Current will be 0.5 ampere. Here voltage is 200, voltage is 300, resistance is 200. Current will be 1.5 ampere. That is simply 300 by 200. Now by KCL, the current here should be 1 ampere because 1 plus 0.5 will be 1.5. Now the other thing that you can use is power conservation. If the auto transformer is ideal, there are no losses. So power output is same as power input. So what is the output power? It is 100 into 0.5 plus 300 into 1.5. So it will come out to be 500 watt. If that is equal to power input, it will be equal to 400 into I input. Why I am not taking cos phi? The entire circuit is resistive in nature, so power factor would be 1. So input current will be 1.25 ampere. So this will be 1.25. Now apply KCL. What is the current in this winding? 0.75. What is the current here? 0.75. Because this will be 1.5. Sorry, this will be 1, so this will be 0.25. So that is how we can calculate the current in different parts of the winding. First calculate load current, then by power conservation calculate input current, and then calculate the winding current by KCL. Is it fine? So that is you can do the current problem. So there can be two problems in auto transformer. One is based on the kVA rating, other is based on current in the winding. The last concept in transformer that can be asked is parallel operation of the two transformer. Now in parallel operation, you have to remember the load shared by one of the transformer is ZB upon ZB plus ZA conjugate ZL into ZA upon ZA plus ZB conjugate. Now what are here ZA and ZB? These are impedance in ohm for the two transformer. They can also be in PU but on same base. This point always remember that you can take impedances in ohms or in per unit, but when you are considering in per unit, the impedances must be on the same base. Is it fine? You cannot take them on different bases. First transform them to the same base. Then the next thing that is sometime asked, if the sharing of load is proportional to rating, then what happens? Then per unit impedances become equal, but these per unit impedances are on their own base. That is the difference. The per unit impedance will be same but on their own base if you want the loading to be proportional to their rating. So now let us see first problem here. It is saying two single phase transformer both have the same voltage rating. That is a necessary condition for parallel operation. They have kVA rating of 200 kVA and 100 kVA. The equivalent resistance and reactance of 200 kVA transformer are 1 and 5 ohm. Equivalent reactance of 100 kVA is 9 ohm. We need to find the equivalent resistance of 100 kVA if the transformer supplies load in proportional to the kVA rating. Now for that we know the per unit impedance of both transformers must be same. What will be per unit impedance of the first one? 1 plus J5 is actual divided by base. What is base? V square by S. What is V square? 11,000 square. Why? Because it is on the 11,000 volt side. By S, S is how much? 200. Similarly here, R plus J9, it is again on the 11,000 volt side, but the kVA is 100. Now this will be, this gets cancelled out. This will be 2. So 4 times, if you square both sides, 1 square plus 5 square is equal to R square plus 9 square. If you calculate R from here, it will come out to be 4.795 ohm. So that should be the resistance of the 200 kVA transformer. The next part of the same problem asks us to find the maximum combined kVA that can be supplied without overloading the either transformer. Now, the ratio of the load sharing is inversely proportional to impedance. So, which one will share more load? Less impedance means more load. So, the transformer having lesser impedance or lesser per unit impedance will have higher loading. So, from here we can easily observe that ZB is greater than ZA. Okay. If you take in per unit, you can calculate the per unit impedance. This is 1 plus J5. It will be root 26 upon 11,000 square by 200. And the second one will be under root 4.795 square plus 9 square divided by 11,000 square by 100. Okay. So this will be around 81. This will be around, let us say, 25. So it will come out to be around 181 plus 25 will be around 106. Or you can say 104. This will be 26 into 4. That will come out to be 104. So that means ZB is greater than ZA, which means the first transformer ZA will get overloaded. Okay, actually both are almost same. So ZA gets or SA gets overloaded. So assign the power equal to its rating to the transformer that gets overloaded. So we know transformer A may get overloaded. So SA will be equal to 200 kVA. Based on that, I have to find SB. How? 200 into 1 plus J5 by 4.795 plus J9. That is SA into ZA by ZB. Because it is inversely proportional to the impedances conjugate. So how much will this come out to be? 100 angle minus 16.737 kVA. Now we know SA as well as SB. Here I have assumed the angle of SB to be 0, but it does not matter much. So the load power will be equal to sum of these two. So if you add these two as phasors, you will get 297 kVA. So that is the maximum load that can be supplied. So remember how to find which transformer gets overloaded. Which has lesser per unit impedance will get overloaded first. Is it fine? So that is how you can determine the overloading and assign that transformer the power equal to its rating, and based on that find the power of second transformer, add the two powers as phasors, you will get the total loading. So that is how we solve such kind of problem. So these are the more or less the kind of problems that can be asked in GATE examination.